Hello and welcome to Math200 Statistics here at Kenyatta College. My name is Ray Lapuz. In this video, we will continue with our Chapter 1 overview. We are in Section 1.3, where we're dealing with frequencies, frequency tables, and levels of measurements. Before we begin, let's talk about rounding off. A simple way to round off is to carry your final answer to one more decimal place than what the data originally has. So if your data are all whole numbers, when you're doing some statistics or finding some values that you need for statistics, you would round off to one decimal place. Also, they talk about, if possible, don't round off in the middle of your calculations. Now, we're going to be relying a lot on technology, so we're not going to run into those types of problems, but if you were to do things by hand, you generally don't want to round off until the very end. So I know that might be a little bit difficult to accomplish, but in general, that's what we want to do. So that's why we really want to rely on technology. Okay, let's go to the next slide where we're going to talk about levels of measurements. So we already talked about the types of data that we can collect. We can collect qualitative data, categorical data, or we can collect quantitative data, which is numerical. Now, when we're talking about levels of measurements, it kind of falls in that category, the idea of categorical and categorical and numeric data can still be broken down into some finer levels of measurement. So there are 4 levels of measurement: the nominal, ordinal, interval, and ratio scales. So let's first take a look at the nominal type of data. A nominal data is essentially categorical. So it's a qualitative type of data, and another important aspect of this is generally you're not able to put this in some sort of significant statistical order. Generally, when you have categories, you can put them in alphabetical order, but statistically that would not really mean anything to your calculations. So for example, when we're putting an order of foods, favorite foods, putting veggie pizza first and vegan sushi second is not really meaningful. Those are just categories. So, well, we're going to be constructing this table to get some idea of comparisons between the different levels of measurement. So in our overview of nominal, we can put the data in the categories, but we can't arrange it in any significant order, and we can't really subtract 2 values. Already, subtraction is going to require you to have quantitative data, and since we're talking about qualitative data, we don't even deal with that. And same for that last column where they talk about the data is a multiple of another. We definitely can't do that because our data is categorical and it's non-numeric. So the next level would be the ordinal scale. Ordinal generally is something that you can put in order. It could still be nominal, but there's no real difference between them. So a good example of this would be an ordinal scale data is a list of the top 5 national parks in the United States. So the top 5 national parks can be ranked from 1 to 5, but talking about the difference between 2 of them doesn't make much sense. So it could still be categorical. It could also actually be numeric when you're talking about the scale, do you agree, disagree? And then you put that in a scale. That is also not really numeric, but definitely there's an order to it. But finding the difference between 2 of those values in the scale doesn't make much sense. So Now we can talk about putting the data into categories, and we can talk about arranging it in order, but the whole idea about subtracting two data values still doesn't make sense, and definitely not a multiple of another. So that's the ordinal scale. Next is interval. So now we're looking at numerical values for sure here, and these numerical values, we're looking at things that can be put in an interval with actual differences between them. So data is measured in an interval scale similar to ordinal, but there's a definite ordering, and there's a meaningful difference between two pieces of data. So a good example of this would be something like the temperature. Finding the temperature where in Celsius and Fahrenheit, the measurement between two temperatures, you can definitely tell a difference between the two temperatures. So the only thing that's now tricky about this is that if you're talking about Fahrenheit, 0 degrees in Fahrenheit doesn't really make much sense. So the freezing point that we know in Fahrenheit is 32 degrees, but then the 0 is less than freezing, and it doesn't really mean much. So the difference makes sense, but the 0 degrees does not mean much, because it's not your different scale. So in terms of looking back at that table, we have the interval data now. We can do the subtraction between two values, the difference between two values, but the idea of 0 doesn't make much sense. Another thing about 0 being included here, or being important here, is that if you are at like 45 degrees and then you double that, because they talk about in the last column, one data value is a multiple of another. If you double 45 degrees, you're going to get 90 degrees. Well, that doesn't mean it's going to be twice as hot or twice as warm when we're talking about doubling or multiple of each other. So the idea of 0 really is important if you're going to want to talk about comparing twice as much of something. And so we get to that last level of measurement, and this is probably the most refined type of quantitative data, and that's the ratio scale. So ratio scale, there's a difference between them, but more importantly, there's a point that's a 0 that can be calculated that is meaningful as an actual value, which means if there's a 0, we can talk about something being twice as warm or twice as hot as something else, or twice as much as something else. And so an example of this would be in multiple choice exam, the scores are given here: 80, 68, 20, 92 out of 100. And so we can see that somebody who got a 20 and somebody got an 80, we can confidently say that this person who got an 80 got 4 times as much as the person who got a score of a 20. And also the other important part is that the 0 is a meaningful score to have nothing there. And so the ratio scale is a quantitative data that has that special meaning. And so in terms of that table that we were creating, here we have nominal, ordinal, interval, and ratio, where at each level it gets more and more refined as a value, as a numerical value. All right, next we're going to focus on frequency tables. Here we have frequency tables. My arrow here just kind of popped up. But in anyways, the idea is that if you have a set of data, we want to organize it, and we're going to learn how to properly organize it in our next chapter. But for now, let's talk about trying to read a table And if you have a set of data that's given here, we have 5, 6, 3, 3, 2, 4, 7, etc. What we can do is we can construct a table that would count the number of values of 2 that we have. So for example, if we want to count how many 2's we have, it looks like there's 3 values of 2, and the 3 values of 2 would represent our frequency. So for the data value of 2, we would say there's 3 of them. We can also count the number of 3's we have. So by the way, after you count them off, you can cross them out because we don't want to repeat our values. So we cross them out, and then we count the number of 3's. In this case, we have 5 of them, and then those 5 values would be your frequency for 3's. So you keep going, and we cross out all the 3's, and then we count how many 4's we have, and 5's and 6's, etc. And then that's how you can make a frequency table. Now remember, there was a dot plot idea for this as well, so this could easily be put as a dot plot, especially with the small amount of data that we have. Now beyond a frequency table, sometimes we're interested in what's called a relative frequency. And so the frequency counts how many values, data values we have. But if you're not caring about the number of data values we have, and you're interested in comparing your data values among each other, we can create this thing called a relative frequency. So relative frequency is essentially the frequency for a particular value divided by the total number. So we have 20 data points that we have in this that we collected. And so for the data value of 2, for example, in the first row, there's 3 of them, and out of the 20 total, we can say 3 divided by 20 and we get 0.15. So 0.15 is 15%. We can look at it as a percentage. And for the data value of 3, there's 5 of them. 5 out of 20 is 1/4 or 0.25. So 25% of your data has a data value of 3. And you can go on and do the rest of this to fill out the rest of the relative frequency table. And then another type of table is called a cumulative frequency, or a cumulative relative frequency. And all that does is essentially add the number of frequencies that you have. Now the bottom line is that for a relative frequency, you keep adding down, so by the time you get to that last number, you're going to get 100%. And so that's the other part. It's an accumulation of your frequencies, or your relative frequencies, as you go down the line. More generally, you can create what's called, more of a frequency table, where your values are more continuous. And so here in this example, they talked about, we don't have the original data, but they say that there's a sample of 100 semi-professional soccer players, and they looked at the heights of these soccer players. So between 59.95 to 61.95, there are 5 players that have that height. So your height is between them. And then there's 3 soccer players that have height that's between 61.95 and 63.95. So in general, you don't want overlapping values. So I think it's pretty safe to say that the reported heights here are given in inches, and then they're given as values with 1 decimal place. So if you look at the way the frequency table is set up, they have 59.95 to 61.95. So those values are to 2 decimal places. And just to avoid overlap, we should not get a soccer player whose height is 61.95, because if you have that height, then you'd be torn between putting it in the first class or the second class. So we'll talk more about constructing these types of frequency tables when we get to our actually in the next chapter, when we actually build these tables. Here we have one final example. They give us the number of deaths in earthquakes that happen in a particular year. So in the year 2000, 231 people died from an earthquake, and in 2001 there's 21,357. And so they can construct a frequency table like this where they count and then they give the total on the bottom. So we can answer the following questions like, what's the frequency of deaths measured from 2006 to 2009? So what we would do is we can look at the table, go to 2006, 2007, 2008, and 2009, and we count all those and we get the total number of deaths. Now, if we want the percentage, we would take the total number of deaths and then we divide it by the total, which is this 823,856. So percentage that occurred after 2009, so we start with 2010, 2011, 2012, and we add all those up and divide by the total. For C, it says the relative frequency of deaths that occurred in 2003 or earlier. So we start with 2000, 2001, 2002, 2003, add all those up, and then if they're asking for a percentage or relative frequency, then we would divide it by the total. Percentage of deaths that occurred in 2004, so you just take this number, 228,802, and divide it by the total. And then you can go on and see the rest of them. So this example is actually in the textbook, and in this textbook you can see the solutions that they came up with. So you can try this out and see it for yourself, and then check your answers and see if they work out. Okay, so again, this is just an overview of some of the things that we're going to eventually see and take a deeper dive into. Right now we're just kind of glossing over it so that we can get an idea of what types of things to expect as we continue on with our study in statistics. All right, that's it. Good luck.